Hello. Hi, Kanan. You are there? Hello.
Yes, sir.
Yes, Kanan. You have raised your hand. You have some doubt. Uh, Hello. I can't hear you. Hello. Can you hear me? Can you just write on chat if you can hear me? If you can hear me, please write on chat. Right now, I can't hear you. Hello. Hi. Kanan, if you can hear me, can you let me know on chat? Anyways, I'll start with how we had planned. So in the previous doubt session, I had told that I'll be discussing on assignment 0, which had been initially shared before the first week, and it contains questions from all the 12 weeks. Right? So, okay. Since there are no questions right now which you want me to answer, I'll start directly with discussion on that assignment. And later on, if there are any questions, I'll wait for a bit to help you out on those questions. Hmm. I'm sharing my screen. Mm. Okay, let's start with the first question. The question is, for bright field illumination, what will we observe? So bright field and dark field illumination are general concepts in microscopy. We had first studied them in optical microscopy, but they are also applicable to TM. And we have seen that in bright field, we have a source of light which is falling on a specimen. And in TM, it gets transmitted, while in optical, it gets reflected in case of a reflection type optical microscope. And so what happens is that as a result of this, all the features which are present in your specimen will usually appear darker, either because they are not reflecting in case of optical microscopy, or they are diffracting your electron beam in TM. So because of that, your background will be of higher intensity, while all the features will be of lower intensity. I hope that will this much explanation was enough for this question. So the correct option will be B, background with higher intensity. And we can also understand this just by looking at the term bright field, since uh, the background is brighter in case we are using bright field. Okay, so moving to the second question. Hmm. Hmm. The mass absorption coefficient of aluminium for X-ray having wavelength of 0.34 angstrom is 0.55. If density is 2.7 gram per cc, then find linear absorption coefficient for aluminium. Mhm. In this question, we have been given the value of mass absorption coefficient uh, for X-rays, and we know the density of the material. We need to find the linear absorption coefficient. So we know that the formula is like this for absorption of X-rays. So I transmitted equal to I naught e raised to minus mu into x, or you can also write this term as minus mu by rho to rho, to take into account the density of the specimen you are using, because more mass, like uh, because usually higher the mass, the more will be the absorption of the X-rays, since there are heavier atoms. So we can, so this is the formula for knowing the transmitted intensity. And as x increases, IT will be getting lower. But in this question, we don't really require this much. We have just been given the value of mu, mass absorption coefficient. Sorry, it's mu by rho. The linear absorption coefficient is mu. Yeah. Oh, sorry, I think it's the other way around. Mu by rho will be the linear absorption coefficient, and mu is the mass absorption coefficient. We'll also confirm this from the slides. Okay, so the previous statement was correct. The one I made later was wrong. Mu by rho is the mass absorption coefficient, which is independent of the state of the material. Higher will be the density, that is more close packed that material is. Higher will be the linear absorption. So no, sorry. Higher, the more close packed the material is, the higher will be the density. Okay. I think I have confused this. Hmm. Okay, I'll repeat again. Mu by rho will be constant for all states, whether the material is in gaseous, liquid, or solid state. And so in this equation, since mu by rho is constant, the higher the density will be, the more the absorption will be, and therefore mu will increase. So higher will be the density, the more will be the absorption. And to get the answer for this question, what we can do is, we have been given this value 0.55 for mass absorption coefficient, which is mu by rho, and we have been given the value of density. So we can calculate mu as equal to 0.55 into 2.7. And I think this, let's see what this multiplication is. It's coming around 1.485. And let's also look at the units. So it was centimeter per gram square into gram per centimeter square. So it will be, sorry, it was centimeter square per gram into gram per centimeter square. Gram per centimeter cube. This is density. This is mass absorption coefficient. So the unit of linear absorption coefficient will be equal to centimeter inverse. So the correct option will be B, between 1.48 and 1.49 centimeter inverse. Also, I had got a little bit confused with the mu and mu by rho, but the conclusion is that mu by rho will be constant for any state of the material, but mu will change. For the solid state, it will be the highest, and for the gaseous, it will be the lowest. So now, if this is clear, we'll move to the next question. The third question is, background intensity for X-ray diffraction pattern is formed due to Let's see it one by one. We know that in case of X-ray diffraction, there is no role of electrons. So secondary electron effect will not be the correct option. Also, OJ effect involves the OJ effect involves emission of OJ electrons, and the incident beam is the electron beam. For example, in SEM, we observe some OJ electron emission, and there also we have electron beam coming. I think there is some network issue. Yeah. I was saying OJ electron emission, we have seen in SEM. It involves an incident electron beam coming, and after that, we can either have a emission of X-ray, characteristic X-ray, or emission of a electron, which is called OJ electron. This is also possible in case of X-ray diffraction when we have an incident X-ray, and that is leading to some events which can cause OJ electron effect, but that will not really be captured by the detector since the detector only captures X-rays. So this will not be the correct answer. Now we have Compton effect and Thomson effect. So we know that the uh, Thomson effect relates to uh, diffraction of X-rays by electrons which are tightly bound to the atoms. So it basically gives you uh, what will be the intensity after scattering as a function of r, the distance from the points of scattering, and theta, the angle of scattering. Let's go to the concerned slides where we had discussed this. Mhm. Mhm. Yeah. Mm. When an electron, when an X-ray is incident on an electron which is tightly bound to an atom, the electron will start to oscillate, and that oscillation will lead to emission of X-rays. And the intensity of it, as I had shown, can be written as a function of small r and theta. And this was the Thomson effect. Also, since the electrons are tightly bound, all the scattering which occurs will be coherent. While in case of the Crompton effect, which involves electrons which are not tightly bound, they are either loosely bound or free electrons. So in this case, the scattering will be incoherent. So what it means is that there will be a phase difference between different X-ray beam that is emitted from the electron from its oscillation. Mhm. Also, there is some loss of energy when the interaction is with a loose or free electron. So the wavelength will increase slightly. So both things are occurring. The X-ray is incoherent also, and the wavelength is also increasing. And this will not produce any interference effects. So because no interference is occurring, it will appear as a constant background in the X-ray diffraction plot. So at all theta angles, we'll see that there is some intensity coming due to Crompton effect, as is written here also. So this will be our correct answer. X-ray diffraction happens by Thomson effect, but the backgrounds comes due to Crompton effect. So our correct option is A. The next question is, what will be the reflections we'll see for body centered crystal structure? Mm. We had discussed in this in the slides in which we covered structure factor calculation. So we had seen that for simple cubic, we'll be able to see all the reflections. That is, all peaks of all planes will be visible. But in case of BCC, only few peaks which have H plus K plus L equal to even will be visible, because for other planes some destructive interference will also take place, due to which there will be no intensity observed for those peaks. So those showing reflection will be H plus K plus L equal to even. In case of FCC also, we had made the calculation, and there we had seen that HKL unmixed give the will give you some intensity, that is, they will have a non-zero structure factor. For all others, that is HKL mixed, we'll not be able to see peaks. So our correct answer here is A. The next question is, the total electron yield for a SEM should be. uh, I was hoping that there would be more participation so that we could discuss some things. Or the electron beam you are using, as well as the atomic number of the atoms in the specimen that you are characterizing. So it can be either more than 100% also, or less than 100% also. But we also know that mm, when you're doing SEM, you want your sample to be neutrally charged. There should be no charge, I mean. So For that, either the sample should be conductive, so that if any charge accumulation is happening, it is immediately getting conducted away, or the electron yield should be maintained such that there is no accumulation of charge. So all the all the electrons which are coming from the beam, they should be going out as either secondary electrons or backscattered electrons, and that would mean that the electron yield will be 100%. So in case of non-conducting sample, we'll have to maintain 100%, or we'll have to gold coat it. But I think for this question, the correct answer should be A, 100%. Question 6. The sample preparation in a SEM requires. Let's see step by step. First is electron transparency. In a SEM, we want to the surface, that is how is the surface of our material, and sometimes we also want to look at the composition, that is do some kind of spectroscopy either using EDS or WDS, and by just imaging the surface, we can also look at some of the features on the surface. So here we are considered specifically with concerned specifically with secondary electron mode. So we are majorly looking at the surface, how the surface is, how its morphology. So we do not want it to be electron transparent, because then there will not be much an emission much emission of secondary electrons, because most of the electrons will just go through. That only is useful in TEM, where you deliberately use very thin samples. Then etching of the surface. Here the method of imaging is by looking at how the secondary electron emission is changing based on the surface or the features you have at the surface. So for that, we do not require to have any prior chemical reaction at the surface. We need etching only for optical microscopy, because there we are concerned with how light interacts with the surface, and by etching we can make the surface rough at those points where there is chemical reaction occurring, like the boundaries in case of metals. So, but in SEM, we do not require anything like this. So this will not be the correct answer. C, minimize surface roughness. So, hmm, hmm. We need to minimize surface roughness so that any kinds of scratches, if they are there on the material, do not affect the image that you're taking. But usually, we want to see the surface features or the specific roughness on the surface. So this also should not be the correct answer, unless we are doing some composition analysis or BSE analysis to see some different phases in the material. Then the fourth option is a predetermined thickness equal to mean free path of electrons. So if the thickness is equal to mean free path of electrons, so mean free path tells you how much an incident electron travels before meeting another electron or interacting with another with interacting with any scattering site or any atom in the specimen. It could be anything with which the electron uh, interacts and changes its path. So that is how we define mean free path. But if the thickness is equal to mean free path, then it's likely that all the electrons will just pass through. They very few will only interact. So this is not the purpose of SEM mode, SE mode in SEM. So this is also wrong. But now, since all the options seem to be wrong, I think the closest option to what is being asked is B, etching, because in case you have metallic samples where you usually want to look at your phases or what are the different phases as well as what are the sizes of the phases. So for that you want to highlight the boundaries that are between those phases. It could be different grains or precipitates. So for doing that, we need to do some etching if we want to highlight those boundaries or highlight some precipitates which have a different chemistry than the matrix. And for that, etching will be useful. And once you have done the etching, the surface will change. It will no longer be as polished as the other places. And the SEM will reflect that change in surface. So the correct answer should be B, etching of the surface. The next question is, in an SEM, characteristic X-rays have the largest sampling volume. Secondary electrons have the largest. Both have the same, and sampling volume doesn't exist. When we were discussing SEM, we had talked about what is sampling volume. So sampling volume was in brief just the volume in the material which mm, the volume in the material from which we get the specific signals which we are talking about. So for example, if it's sampling volume for secondary electrons, it will be somewhere close to the surface. So from this region on in the specimen, the secondary electrons will be able to get emitted and get detected by the detector. So this is the sampling volume for the secondary electrons. While for the backscattered electrons, it's more likely that the sampling volume will be much larger. So backscattered electrons, since they have higher energy and can come out from much deeper in the sample, the volume from which they are coming is large, and so we'll say the sampling volume is large. For X-rays, it's usually somewhere in between. So let's say this is for X-rays, the one in blue. And since X-rays are more penetrating and have higher energy, they are able to come out from deeper in the sample than the secondary electrons. Secondary electrons have much lesser energy, usually less than 50 electron volts. So we had studied this. So the correct answer will be characteristic X-rays have the largest sampling volume, I think. Hmm. Let me just check the exact order. Mhm. Okay, I had the secondary electron has the smallest sampling volume, as can be seen here. Backscatter, it's around 100 nanometer. Backscatter electrons have around 500 nanometers, while characteristic X-ray have around 1 to 3 microns. So I had interchanged BSE and X-ray. So it's SE less than BSE less than X-ray. X-ray will be more penetrating than the backscattered electron. So that was my mistake. So here I'll just correct it. Mm. The next question is, in electron microscope, the electron source could be. Mm. We have studied about different mm, methods of generating electrons for being utilized in electron microscopy to investigate our specimens. So there we discussed thermionic generation, field emission generation, and what are the differences between both of these. In thermionic, we had seen that it's because of the heating that the electrons are getting. You can say the heat is so high, the filament gets heated to such a high temperature that electrons start getting expelled from the atoms, and as a result, we get emission of electrons. In field emission gun, the difference is that we use a very high electric field to draw out the electrons from a very thin needle, like it's needle like tip. From that we are drawing out electrons, and this this is actually much gives us a higher intensity of electrons as well as much more monochromatic beam. So a field emission gun is preferred when doing microscopy, but both are used, especially in SEM both are used. So the correct answer should be C. Hmm. Hmm. So let's take a 5-minute break before moving on with the rest of the questions. Till then, if you have any doubts, please write it in chat. Okay, let's continue with the questions. The ninth question is chromatic aberrations can be corrected by. We know chromatic aberration occurs because the beam that is incident on the lenses is made of multiple wavelengths. It's not made up of a single wavelength. And since every wavelength will have a different focal point, there will be some dispersion that will be observed. Right? So for two different wavelengths, we'll see two different points at which the beams will focus. So this is called chromatic aberration. Uh, this cannot be corrected with perfect shape and proper alignment. Spherical aberration can be corrected by, to some degree, by improving the lenses. Semi angle of the aperture. Mm. So again, aperture can help with spherical aberration, but not with chromatic aberration, because this has to do with the wavelength of the incident beam. Using a large aperture, so this also won't help. But if we use monochromatic wavelength light, then we will only have single wavelength. So chromatic aberration will not occur. All the incident beam will focus at only one point. So our correct answer should be D. Question 10. When using copper source as radiation, the best filter material would be. So when we were studying about filter materials, we were studying related to the topic of absorption of X-rays, and we had seen that for every material we have a K alpha H. So if we plot the absorption mu by rho, this is the mass absorption coefficient versus lambda, the wavelength. The higher energy electrons, mhm, sorry, the higher energy X-rays will get absorbed more. Sorry, the lower energy will get absorbed more, while the higher energy will get absorbed less, because it is more penetrating, and it will interact less with the atoms in the specimen. So usually it's something like this, but at some particular lambda, we see a increase and then again a decrease. Let's go to the concerned slides and also look at it. Mhm. Mhm. So at a particular lambda, we see that there is a sudden increase in the absorption. It is called the K absorption edge. And what is happening is that at higher lambdas, the as we go from higher lambda to lower lambda, as the energy of the incident X-ray increases above a certain value, it is now able to eject the electrons from the inner shell. That is, if this is a K edge, then it is able to eject electrons from the K shell of the atom. And since now the incident X-rays are being utilized into ejection of electrons, the absorption is much higher. There will be less diffraction taking place. And as a result, uh, we'll see a peak in the mu by rho versus lambda plot. And this can be useful when selecting a filter material, because normally we see multiple peaks from any source. For example, in case of copper, we'll have a K alpha peak, which corresponds to characteristic X-ray from L2 K shell, which will have energy corresponding to L2 K shell. But we also have K beta, which is from L2K for some other orbitals of L, and therefore it's difficult to get monochromatic X-ray generation. But if we use some filters, we can filter out the other wavelengths. For example, we can filter out K beta, and actually K beta will be difficult to filter out because it has a very close wavelength to this, not erasing. Anyways, yeah, I was saying the K beta has a wavelength which is very close to K alpha, so it is difficult to filter this out. But others, such as L, uh, okay, I had got confused. So K beta is from M to K. I had got confused here. So K beta is from M to K and K alpha is from L to K. And K beta has a higher energy than K alpha, since the de excitation from occurs from a higher shell, the M shell. And as a result, if we want to remove K beta from the copper source radiation, then what we can do is we can put a filter material which will able to absorb the energy from K beta, but it will not absorb K alpha X-rays. And this can be done by usually using an element which has atomic number 1 or 2 less than the one which was used as the source. So here, if it is copper, we can use something which has 1 or 2 less atomic number. For example, nickel can be used while zinc cannot be used. And what now will happen is that if we use nickel, the K beta X-rays which are generated will be absorbed by nickel to uh, will be absorbed by the nickel atoms, and they will knock out the K shell electrons from the nickel atom. As a result, we'll have a K edge in the filter material, which is nickel. But K alpha X-rays coming from copper will not have enough energy to knock out the K shell electrons of nickel. As a result, K alpha will not get absorbed. That is why nickel will be a suitable filter material for copper. Now we can move to the next question. Which of the lens is necessary for an optical microscope to collect the source signal and direct them over a small area on the specimen surface? Mm. So let's look at the options. It can't be D because optical microscope only has optical lenses. It does not have have electromagnetic lenses because in optical microscope we are not dealing with charged particles, we are dealing with light. Projector lenses are only in TM, we don't have them in optical microscope. Then condenser lenses are used to uh, kind of converge the light which is coming from the source so that it can be later on used for illuminating the sample and doing the imaging. So uh, this has the purpose of just converging the incident beam which is coming from the source, while an objective lens is used to converge the beam even further so that we can get a magnified image from the, in case of a reflection type microscope, from the reflected light. And based on the strength of the objective lens used, we'll have different magnifications in the final image that is formed. So the answer should be objective lens because this is the lens which directs the light over a small area on the specimen surface. And based on how much it is converging, based on the lens strength, the magnification will change. Let's move to question 12. If an electron from M shell fills the hole in K shell, the radiation is called. So we already saw it here when I was explaining about filters, that K alpha corresponds to L to K shell and K beta from M to K shell. So M is the third shell, while K is the first shell. And that's why the radiation will be called K beta. M alpha will mean that it comes from, let's say, N shell after M to M shell. So that will not be the correct answer. Neither will K alpha be the correct answer. The correct answer will be B, K beta. Question 13. What is the source used in WDS, wavelength dispersive spectroscopy? Mhm. In WDS, we have a incident beam of electrons. It could be as an attachment to SCM set apparatus or a EPMS apparatus. So we have an incident beam of electrons, which is uh, falling on the specimen. It is interacting with the atoms in the specimen. Then the characteristic X-rays which are emitted from the specimen are being detected by a WDS detector, and that is how we are uh, getting to know the composition of our specimen. So the correct answer should be mm, characteristic X-rays, because by uh, measuring the in WDS, we are measuring the wavelength by using diffraction, the principle of diffraction. So for those wavelengths for which we are observing diffraction, sorry. So we have some single crystals in the WDS setup, and for those angles for which we are seeing diffraction, from those angles we can calculate what is the wavelength of the X-rays that are coming, and from that we can tell what is the atom from which it is coming. So the correct answer will be characteristic X-rays. These are the signals which are used in WDS. Next question. In XRD, peak broadening occurs in polycrystalline materials due to it will not be due to presence of no strain. If there is no strain, then we won't see any peak broadening. We'll have perfect diffraction, Bragg's diffraction. So we'll only see very sharp peaks. If we have uniform tensile strain, then there will be increase in the lattice parameter uniformly, and that will lead to shifting of peaks, but it will not lead to broadening. This is also not the correct answer. Here, uniform compression strain, this will also lead to shifting in the other direction since we are compressing the atoms together and lattice parameter is decreasing, but it will not cause broadening. If we have non-uniform strain present in grains, then at some portions locally we'll have a decrease in the interplanar spacing, and at some other portion we'll have an increase in the interplanar spacing due to the non-uniform nature of strain. As a result, we'll see that the peaks will become broader. There will be smaller peaks at angles which are slightly different from the perfect Bragg's angles. So as a result, we'll see that there is some kind of broadening taking place over some theta range. So let's say this is the theta. The correct answer will be D. Question 15. In differential interference contrast mode, DIC, compositional contrast is produced, depth perception is produced, fraction pattern is produced, or fluorescence contrast is produced. Mhm. We we have already studied that in differential interference contrast mode, it is the change in the path difference of two different beams, two different rays, which are traveling through a specimen. But there's a change in path difference due to different thicknesses and refractive indices of different regions in the specimen. And as a result, these then get converted into change in the mm, so these are then converted in some way to change in colors which we see in the image. And so the correct answer should be that we observe the change in refractive index or thickness in the specimen. But that is not in in the options here. So we know that fluorescence is not correct. Diffraction also is not taking place here. Hmm. Composition contrast can be there, or depth perception can also be produced based on the difference in the refractive indices or thickness of the different regions in the specimen. So let's look at the slides one to refresh our memory. Hmm. Yeah. So the minute differences in the specimen thickness gradients and refractive indices can be studied. Mm. And based on the optical difference between the two rays which go through the specimen, we are able to generate this kind of an image having different colors. So we have a Valencian prism. Well, I think it's, yeah. So we have this prism which recombines the incoming polarized lights into same polarization, and then we are able to get the image. Also, if we look at it, it can also give some depth perception. If the illumination is oblique, and due to some either constructive or destructive interference taking place, it is possible that there will be appearance of some three dimensions in your image. So the correct answer will be depth perception. Last question 16. In fluorescence microscopy, white light is used as a source, electromagnetic radiation is used as a source, light of fixed wavelength is used as source, or none of the above. Hmm. So we know that in fluorescence microscopy, there are some fluorophores which are applied on our specimen, and when a light is of specific wavelength that's shown on it, then some excitation occurs, and during the de-excitation, we have emission of visible light, which comes out as fluorescent colors. And based on which of the portions of the specimen have the fluorophores, there will be um, fluorescence in those portions on the specimen. Mm. Let's look at uh, the setup of fluorescence microscopy in detail. Mhm. So we have hello, Om Prakash. You have any question?
No questions.
Okay, so I was discussing the 16th question. We had, like, I had discussed all the previous questions before it. I just show you for reading it once. So in fluorescence microscopy, what is the source of the what source is used? Okay, so we were looking at the setup of the apparatus, and here it's written that light of a specific wavelength gets absorbed by the fluorophores, and this causes them to emit light of longer wavelengths, which is then seen in the image. For this, we use some light source such as some xenon arc lamp or mercury vapor lamp. But for this fluorescence to occur, the molecules of fluorophores, which we are using, here we have seen, right? Then there are certain molecules which will give rise to this fluorescence process, and they require a light of specific wavelength only. So this will be the source that we use. So I think the correct option should be C here. Light of a fixed wavelength is used as source. With this, our assignment discussion is completed. If there are any other doubts, you can let me know now, or any suggestions you have, since this was the last session. This was an extra session that I took. The previous 12 assignments have already been discussed. So any suggestions before we close this course will be welcome. Okay, so if there are no questions, we'll end it. So before that, I'll also just mention that I'll be sharing a feedback form in the discussion forum, which will be uh, for this problem solving sessions only. So there I'll request you all to write your honest reviews on how you found these problem solving sessions, which were conducted every Saturday. And since I'll likely be conducting them for the subsequent courses also, which will be happening maybe
Nothing
next
else.
year. Okay, nothing. Anyways, I'll be sharing the feedback form. So I'll request you all to give me some suggestions or honest reviews on how the problem solving sessions can be improved for the future. So let's wrap up now. Thank you for attending. Goodbye. Also, I know that you'll be having exams soon. So if you have any doubts, you can post it in the discussion forum. I'll still be looking at it every once in a while, and I'll try to answer whatever queries you have. Thank you.